Good day to all of you. My name is Nitin Tomar, and I am a Prime Minister Research Fellow in the Department of Mathematics at IIT Bombay. Today, we are going to discuss some problems from linear algebra, calculus, analysis, and topology, some basic problems from these areas. So, the first problem is which of the following subsets are true under the which of the following statements are true under the usual topology on R2. So, we are given five sets and we have to find whether or not the given sets are open or closed. So, one important result that we are going to use is the following, that inverse image of an open set under a continuous map is an open set in the domain. So, and the same thing holds for the closed set. Now, the first option is this is the first option. So, the first is, so we are denoting this first by omega 1. So it is the set x comma y in R2 where y varies from 1 to 2 with strict inequality. Now if we define the function f1 xy equal to y, then we know that it is a continuous function from R2 to R. It is a real valued function continuous on R2. So now omega 1 can be written as f1 inverse of 1 comma 2. So this is the thing. We have written it here. So omega 1 is f1 inverse of 1 comma 2. That is inverse image of 1 comma 2 under the map f1. Now f1 is continuous and 1 comma 2, this interval, open interval, is open in R. Therefore omega 1 has to be open in R2. Okay. So similarly, for the fourth and fifth option, we can define the appropriate function and use these the similar facts to prove that these statements are indeed true. So the first statement is true. Now if we look at the fourth set, so the fourth set is omega 4, which I have denoted x comma y such that x square plus y square equal to 10 is closed in R square. Graphically speaking, it is a boundary of this, it is the circle. So any circle is a closed set, okay, because it is closed. Yeah, I mean, the one way to see is we have to prove that this is a closed set. So you define a function f4, which I have denoted this x square plus y square. Again, it is a continuous function from R square to R. And since singletons are closed sets in the real line, so this omega 4 can be realized as inverse image of 10 under this map f4. So it will be closed in R2 again. And the same logic goes for the fifth part also, where now you have to choose your function x square plus 2y square. Then omega 5 can be written as the inverse image of 3 comma infinity, close 3 comma infinity under this map. So it will be closed. Now let's go to the option number second and third. So the second option is x comma y such that x plus y lies between 1 and 3 with strict inequality from 1 and slack with 3. So I have drawn the graph. It's easy to see by the graph. So this is the graph. Hmm. So as you can see in the graph, if you choose any point from the, so for the second part, if you choose any point from the boundary, then a set is open if and only if you can push a neighborhood around any point in the set, and that open neighborhood should be contained in the set itself. So if you, as shown in the blue, if you take any point here, for example, if you take any point here, then no matter how we choose our open set, we will not be able to push this region, this open set, inside the shaded region, which is shaded by red. So the second is not in omega 2 is not an open set. Similarly, Omega 3 for the third option, omega 3 is not a closed set. Why? Because its closure will have both less than equal to, whereas omega 3 have strict inequality from the first side. So hence it is not a closed set. Now let's move to the second question. So the second question is about the sequence of function. So we are given two sequences of function fn and gn on 0 comma 1. So where fnx is this x power n and gnx is just x by 2n. So the question is, which of the following statements are true? So first is fnx does not converge uniformly on 0 1. So okay, and this is, no, this statement is just a minute. So fnx does not converge to uniformly on 0 comma 1. This statement is true. Why? Because we know that if there is a sequence of continuous, see, the point is each fnx x power n, it is given by x power n, it is a sequence of continuous function on 0 1. So if it converges uniformly to some function, let's say f, then that f has to be a continuous function. So where if you compute the limit function, it will be this fx equal to 0 when x is between 0 and 1, or x is equal to 0, and at x equal to 1 it is 1. So clearly this function is, so f is not continuous, f is not continuous. So this is my limit function, and with this f is not continuous at x equal to 1. So therefore f cannot, this sequence of function cannot converge uniformly to f. Okay. Now the second option is whether you can interchange the limit and integration. So we compute the LHS. So LHS is limit fnx dx, limit integration fnx dx. You put the value, so we will get this xn. So when we integrate, we'll get 1 upon n plus 1. So its limit as n goes to infinity is 0. So the left hand side is 0. And RHS also, see, okay, let me do it. On RHS, so so this is nothing but 0 to 1 f of x dx. So f is 0 except for the point x equal to 1. But the Riemann integration does not change when you change the values at finitely many points. So this value will be taken 0, and hence this function will be 0. So the when you are changing the limit and the integration, the answer is same. Okay. So in the second option, inequality is given, but they are in fact equal. So the second option is false. Now in the third question, we have to see whether or not this new sequence sine 2 pi x fnx. So this is the new sequence sine 2 pi x fnx, whether this converges uniformly on 0 comma 1. We'll prove that in fact this is the case. So remember that if fn, so this is supremum test. If a sequence converges uniformly to a function f, if and only if this supremum norm, which we call this supremum norm, converges to 0 as n tends to infinity, where this fnf norm infinity means supremum of modulus of fnx minus fx such that x varies over closed interval 0 comma 1 and its supremum. Okay. So let's calculate. See, when x is, so the first case is when x is between 0 and 1 with 1 not included. You see that because x power n goes to 0 as n tends to infinity for all x between 0 to 1. So in the first case, everything will go to 0 as n tends to infinity. The trick is, see, in the earlier when sine 2 pi x was not there, the limit was 1. But here when you put x equal to 1, the sign will contribute to the 0. So the sign will become the 0. So sine 2 pi x will be sine 2 pi and limit fnx, which is 1. So it will be 0 itself. So it, it will be it will be sine 2 pi 1 power n So it is actually 0. So in either case we are having that this supremum goes to 0. So hence this limit, so this converges uniformly to 0. Okay, not only it does converge uniformly, it converges uniformly to 0. So the third option is true. Now we were also given another sequence gnx x by 2 power n on minus 2 comma 2. So the fourth option is whether or not this gnx, sorry, third option is whether or not this gnx converges uniformly on minus 1 comma 1, or what about minus 2 comma 2. So one can see that on minus 1 comma 1, mod of x by 2 is less than 1. So hence x by 2 power n goes to 0 for all x between minus 1 to 1. So again by this supremum test, Gn converges uniformly on minus 1 comma 1. So the uniform convergence is guaranteed on minus 1 comma 1. See, but on what happens on minus 2 comma 2, this Gn of minus 2, if you put, then it is minus 1 comma n. So this is not even convergent. Okay. So the D option is true actually. It converges uniformly on minus 1 comma 1, but not on minus 2 comma 2. Now the fifth option is whether or not this series summation gnx converges for every x. As we have just seen, it is not true. Why? Just because we have to put x equal to, let's say, minus 2 again. So if you put, if you consider this series and you put x equal to minus 2 in this series, this series will become summation minus 1 power n, which is not convergent. Okay. Now the same question is asked for the summation fnx upon n factorial, in the sense that whether or not the series of functions, so we are on the this fifth and the last option, whether the series fnx upon n factorial converges uniformly on the compact interval in real. See, if you put fnx, just a minute, yeah, if you put fnx, then you will get this series. Okay, and this is a well known series of e power x. So this series, yeah, so this series converges to e power x, and via Weierstrass test one can prove that indeed this series converges uniformly on a compact set. Okay, so the fifth option is actually true. So the fifth option is true. Now the third question is from linear algebra. So we are given a transformation x comma y goes to x plus 2y minus 2x plus y. So the first question is the collection of all those xy for which t maps them 0 comma 0, they are infinite, which means kernel t has infinitely many elements. It is not true. One can solve using the definition only. If txy equal to 0, if t of x comma y equal to 0 comma 0, then this is possible if and only if x plus 2y is 0 and minus 2x plus y equal to 0, which is possible. So this is a system of linear equation in two variables. So if you solve it, we'll get x equal to y equal to 0. So the only possible point where t of x comma y is 0 0, it's the 0 0 itself. So there is only one point. So the first option is false. First option is false. One can easily check using the definition of linearity. What is the definition of linearity? That the sum splits, in the sense t of z1 plus z2 equal to t of z1 plus t of z2. And second, you can pull the scalar out. And this is true. One can directly check. Now the question is, when we consider R square as a C vector space, how do we consider? If x comma y belong to R square, we can have x plus iy in the complex plane and vice versa. So from here to here we can go, and from here to here we can go. Then the question is whether or not T is C linear. Okay, so C linear means the scalars you are pulling out, they should be from the complex plane, and you can check that this is also true. just because t is simple, it's a linear, I mean, it's a matter of checking, nothing else. Now, the fourth question is a in general statement that I have written down, that every C linear map T. So this is my fourth statement. Okay. Every C linear map T from R2 to R2 is R linear. So if it is a C linear maps, which means you can pull the scalars for all complex plane, right? So in particular, R is a subset of C. So you can do that for the real line also. So hence every C linear map is an R linear map. Now the fifth question is the converse. Whether every R linear map is a C linear map. And intuitively, it should be clear that the answer must be no. Why? Because R is a smaller subset. R is a strict subset of complex plane. So if you are able to pull some scalars from the smaller set, it does not mean that you will be able to pull scalars from the bigger set. So, from one concrete example is this: T of A plus IB is minus A plus IB. So, this is an R linear map, okay, but it is not a C linear map. Why? Because if it is, then T of iota by definition it should be 0, right? But T of iota, it can be written as iota of T of 1. But T of 1 by definition is minus 1, so it should be minus iota. So T of iota is having two different values, 0 and minus iota, which is not possible. Okay, so this is not a C linear map. Now the fourth question is from calculus of several variable. So we are given a function on R2, a real valued function, which is defined at origin as 0, and otherwhere else it is a rational function xy upon x square plus y square. Now the first question is whether the partial derivative. Okay, let's first go for the fourth question. Yeah, sorry. Let's start with the first option itself. Whether the partial derivative at 0, 0 exists. So what is the definition of the partial derivative? It is this, right? Del f by del x at any point x comma y, it is limit f of x plus hy minus f of xy by h, and as limit x h tends to 0. Now you plug in the value and we will get that del f by del x 0 comma 0 is actually 0. So the first option is true. Similar thing can be done for, okay, let me do. So the similar thing can be done for this 0, the partial derivative with respect to y. So how will it change? It will be 0 comma h minus 0 0 again h. So you plug in the values and you will get the zeros. So this is also true. Now whether or not del f by del x, we know that 0 at 0 0 this value exists. So now the third part is whether this partial derivative function, again it is a function of two variable, whether or not it is continuous at 0 0. So the answer is false. We'll see why. So del f by del, just a minute. Yeah. So del f by del x at x comma y, we compute by the definition and it will be this. Y, this rational function. Okay. Now my claim is just a minute. So let if possible this is continuous. Okay, we are assuming on the contrary that this is possible. So if del f by del x is continuous at 0 0, you multiply it by any continuous function, product of two continuous function is continuous. So g times del f by del x, it should be continuous, where g is the projection onto the first component, g of x y comma g of x comma y equal to x. Now this is a continuous function. So g times del f by del x should be continuous at 0 0. And if it is continuous at 0 0, we know that it should be equal to 0. Why? Because if it is continuous at 0 0, then this limit g del f by del x as xy goes to 0 0, it should be g 0 0 del f by del x at 0 comma 0, which is 0, right? Now if we compute the limit, so we just plugged in the values. Now if we put y equal to mx, why? Because if this limit exists, x comma y goes to 0 0, it should be equal to from any direction the in which x and y is approaching 0. So in particular from any line also. The equation of line is y equal to mx. So this, if we put this value, then we'll get limit x goes to 0, m upon m square minus 1, m times m square minus 1 upon m square plus 1 the whole square. Now this limit clearly is not 0 for, let's say, m equal to 2. So this is not a continuous function. So our assumption that del f by del x is continuous, it's false. Okay. So this is not true. Now the fourth. So similar thing can be used for fourth to prove the continuity. You go via the direction y equal to mx. You plug in the value and you will get m upon m plus m upon 1 plus m square. And if the limit exists at 0 0, then it should be equal to f00, which is 0. But clearly you know that if you choose m equal to 1, then it need not be equal to 0. So this is a contradiction. Yeah, so sorry for the spelling mistake. So this is a contradiction. So hence it is not continuous. So fourth option is false. If it is not continuous, then it is not differentiable also. So this is also false, because every differentiable function is continuous. Okay. Now the next question. Yeah. Yeah. So the next question is, which of the following statement is true and x is a non-negative real number? So the first part is we use the derivative under the integral sign. Okay. So for the first part we use this formula, uh, which is given by this. Just a minute. So derivative of the integral is actually given by this formula, where where phi is a differentiable function on I and g is continuous. Okay. So if you plug, so in the first part, f of x is given to be integration 0 to x t square plus sin t dt. So in this case, our phi x is equal to x and g of t equal to t square plus sin t. If we plug the values in this formula, you will have f prime x will be x square plus sin x. So the first option is true. So the first option is true. Now for the second, we know that this limit function was x power n, right? The sequence of function was x power n and its limit was this 0 1 when x is less than 1, and when x is equal to 1 it is 1. Hmm. Now if you compute this value, now define fx. So here we have been given this fx equal to this. So if you compute this value, so for any x, even 0 or 1, it, because f is, this small f is 0 except at the point 1, and Riemann integration does not change. by changing the values at finitely many points. So this small f of t can be replaced by the zero function itself. So this value will be 0. So this will implies that f prime x is 0. Okay. So then this is not true. F prime x, capital F prime x is not small fx, because capital F prime x is 0 for all x. But f of x is not 0. F of small f of x has value 1 at x equal to 1. So this is false. So this is not true. Okay. Now for the third question is interesting. Now we have a function on 0 to 2, a real valued function, and it's the greatest integer function. Greatest integer function means, okay, if you imagine a real line, you take a number and the integer closest to the left of it is the greatest integer value. For example, if you choose 1.5, its greatest integer value will be 1. If you choose let's say 0.2, then it will be 0. Even 0.9 will have 0 as the greatest integer value. So then this capital F of x is defined as the integration of this greatest integer function. Now we have to check whether or not f is differentiable. Okay, so let's check. So f is this greatest integer function, and capital F is defined as this integration function. Now we consider, because we have to check differentiability, we have to first go for the continuity. So we'll check for x in the neighborhood of x only. So for x less than 1, we'll have f of t equal to 0, right? Because for all t between 0 to x and x is strictly less than 1, the greatest integer will be 0, right? So in that case, our integral function will be 0. The capital F will be 0. At x equal to 1, f of 1 by definition will be equal to 0 to 1 greatest integer function. Now again, this is the same thing that we have discussed before. This greatest integer function between 0 to 1, it has value 0 except at the point t equal to 1. Whereas everywhere else it is 0. And Riemann integration does not change by changing the function value at finitely many points. So it is 0 because f is 0 except at one point. Now when x is greater than 1, okay, when x is greater than 1, then fx by definition is 0 to x f of t dt. We can break it into two parts, 0 to 1 and 1 to x. So 0 to 1 part will be 0, obviously, by using previous calculation, and we will be left with this part. Now when f of t is between 1 to x, then the greatest integer value will be 1 if x is strictly less than 2. Anyway, we have to choose in the neighborhood of 1, so we can choose x strictly less than 2. So this will be actually 0 to 1 1 dt. Sorry, the limits are 1 to x. So the answer will be x minus 1. So finally we'll have this f of capital F of x is 0 when x is less than equal to 1. When greater than 1 less than 2, this f of x is x minus 1, which is, just a minute, just a minute. So we have found out that fx, capital F of x is 0 when x is less than equal to 1, and when x is between 1 and 2, it is x minus 1. Now if you draw the differentiability, means there should not be a sharpness at the point. So if you draw the graph, then we'll see that if there is 0, it is 1 and it is 2. So between 0 to 1, so this is x-axis, this is y, and I'm drawing the graph of f of x. So from 0 to 1 it is 0, and then it behaves like this. So, so at this point it is not differentiable, and by definition also one can check. So this f is not differentiable at x equal to 1. So this option is also false. Oh no, no, this is given that this is not differentiable. So which means it is true. F is not differentiable, right? Yeah, this is true. Now it is given that on some open set U, f prime x is 0. Then does this mean f is a constant function? Which means derivative is 0, then it is a constant function. It is true unless of course you're starting with I mean you have to start with a connected open set also. So for example, if we take f of x to be 1 2 and x between 0 to 1, let's say, and x between 2 to 3, then you can clearly see that if you take u to be the union of 0 comma 1 and 2 comma 3, it will be open set. F is differentiable there, and in fact f prime x is 0 because f is 1 and 2. And so but f is not, capital F is not a constant function, so this is not true. And for the last part, again one can use the derivative under the integral sign because the integrand is continuous now. So so f so if you use the derivative under the integral sign, it will be f prime x will be f of x. And now it is given that f prime x is 0, so which means f of x is 0. So this option is true, right? F of x is 0 for every x. In particular, f of x is equal to f of 0. So this is true. Now the last question. So the last question is easy because it's just differentiability. But anyway, it's a good question. So f of x is given to be as when x is 0, it is 0. When x is not equal to 0, it is e minus 1 by x square. So first option is whether or not this function is differentiable. So we can use the definition of differentiability, right? So we if so at 0 0, so f is differentiable if and only if this limit exists by definition. Now we compute this limit and we'll have limit x tends to 0, 1 upon x times e 1 by x square. And as x goes to 0, this limit is 0. So f is differentiable at 0. So first option is wrong, second is correct. And for the third part, it says the Taylor series of, so f has a Taylor series at x and it's convergent to f of x. So for that we will use the Taylor series of exponential function. Okay. Now what is the Taylor series of exponential function? So it is e power x is summation xn by n factorial. N goes from 0 to infinity. So if you put x replaced by minus 1 by x square, you will have this when x is not equal to 0, and when x is 0, we'll have 0. So at any point it has a Taylor series which is convergent to f of x. So this is true. And the fourth question is the Taylor series of f around the point x equal to 0 converges to f uniformly. So let's find out first of all the Taylor series of f around x equal to 0. So what is the formula for that? So around the point, the Taylor series is given by nth derivative at that point, which is 0 in this case, then x power n and n factorial. Now one can check that the nth derivative of this function, which we have been given, is 0 for all n. So for all n greater than equal, for all n in n naught. for all natural number. So hence this series will turn out to be 0, okay, in some minus epsilon to epsilon, where epsilon is some positive number. But f is not 0 in this interval, in this minus epsilon comma epsilon interval. So this last option is false. So we are done with the assignment.